Hello, my name is Steve Bowler, and in this video we're going to be taking a look at Border Gateway Protocol, otherwise known as BGP. We are going to take a look at the foundations of BGP and a lot of different topics. We're going to set up different BGP connections, we're going to set up external BGP, internal BGP, and we're going to take a look at some of the BGP attributes. BGP is run in between different autonomous systems. What we have is customer 1, we're going to put in AS100, and the ISP R1, R2, and R3, those routers are going to be run in AS200. So usually you would not be running BGP if you had just one connection out to your service provider, if you were just single home. But as we can see in this case, we have two different links, are what's called dual home connection to our ISP network. So it gets a little more complicated when we have to set up BGP and prefer one path over another. That's when our complex BGP route manipulation comes into effect, and we have to do that. So BGP is very scalable, and well, of course it scales the internet. So we have two connections from customer 1. We have a primary link which is going to simulate a T3, a 45 meg circuit, and then we have another backup circuit we're going to use, and that's going to be our 1.5 meg circuit, which is going to be our T1. So just to let you guys know, we have already set up all the IP addresses, the interfaces, the loopbacks, all of that stuff in this lab. So let's go under customer 1 and take a look at the basic configuration of BGP. We're going to type in the command from global configuration mode, router BGP, and then we're going to follow that up with if we type in a question mark, you're going to see it's going to be looking or asking us for an autonomous system number. So for customer 1, we're going to put him in autonomous system 100, and this is going to start the BGP process on the router. So our next configuration under BGP is to put in our neighbor statements. We have to peer to other routers to form neighbor adjacencies with them. So both sides have to be set up. So two neighbors have to peer to another. So it's not like in IGP where you can just specify a network statement and then it'll go out and form adjacencies automatically. Within BGP, it has to explicitly be set up on both sides, on both routers. So we're going to put in our peers. So we're going to peer to ISP R1 first. We're going to put in the neighbor statement to do this, and then we're going to put in the IP address of the far end connection, which is ISP R1's link, which is 130.0.11.2. If I do a question mark after that, we have a bunch of options that we can do under BGP, which makes it very scalable. But what we're going to do is we're going to use the command remote AS, and then we're going to be putting in the AS in which we are peering with ISP R1. So autonomous system for ISP R1 is 200, and this type of neighbor relationship that we are trying to form is an external BGP neighbor. An internal neighbor relationship within BGP, or an IBGP connection, would be the ISP. They are running IBGP internally between two routers within the same autonomous system number. That is a IBGP neighbor. So two routers peering to each other within the same autonomous system. However, this link is a external BGP peering. So the next thing we're going to do on customer 1 is we're going to type in our neighbor statement for our BGP peer ISP R2. So again, we're going to type in their far end IP address, which is the 12.2, and then we'll specify the remote AS of 200. Again, like I was telling you guys earlier, we use BGP to advertise our networks out to other autonomous systems. And those autonomous systems that we advertise to will advertise our networks out to other peers. So what we can see is that the internet, if it is running BGP, is made up of a lot of different autonomous system numbers, and all these ASs share networks between each other. So now that we have our neighbor statements, we have to tell BGP what networks we want to advertise to these neighbors. So to do that, we're going to be using the network command, but the network command is not like the network command in the IGP world. So where you set up a network under OSPF and specify the subnet that will go out and form neighbor adjacencies with other routers. This network statement specifies, under BGP, specifies what subnets we want to advertise out and what networks we want to advertise out to our BGP neighbors. Again, we're going to do the network command, and then we're going to put in our network 130.0.1.0, which is our loopback 1 interface, and then we're also going to need the mask statement for our subnet mask on this network, which is, as we can see from the diagram, a /24. And then we are also going to add in the loopback 2 interface, which is the 2 network on customer 1. You have a BGP topology table, then you have also an IP routing table. So in order for these networks to be advertised out to BGP neighbors, we have to have a connection in our routing table that matches specifically this prefix in which we are specifying under BGP with the network statement. So if we do a show IP route on customer 1, we have to have these network, we have to have the subnets in our routing table to be advertised, for it to be advertised into our BGP table as well. So we can also take a look at BGP authentication. It is pretty simple to set up. If I go under customer 1 and do a router BGP 100 and go and specify our neighbor 130.0.11.2, what we can see is we have a password statement or a password option, and then we can just specify the password as Cisco in this case. So BGP authentication is relatively simple. Just one neighbor statement to your neighbors that you're peering with using authentication, and you should be good to go. So we're going to do in this case ISP router 2 and ISP R1 is what we're going to be performing BGP authentication with. So let's go to the ISP routers and take a look at those. If I do a show IP route, we are running internally. The IGP is OSPF, between the ISP network, so R1, R2, and R3 are running OSPF internally to reach all of the loopback networks and links between the routers. So again, just want to let you guys know that that is already pre-configured in this lab. Let's do ISP R2 first. Again, to enable BGP on the router, we're going to put in router BGP 200. That's the local AS. Then we're going to put in our neighbor statements. And we're going to be peering with, first we'll peer to customer 1, so neighbor 130.0.12.1. And this is an external BGP connection, so we'll put in the remote AS as 100. So again, that is not our AS on R2. Our AS is 200. We are peering with a remote AS of 100, and that is a external BGP connection. So let's go ahead and do a debug IPBGP events, and let's see if we can get some good information from this output. So with this debug, it's not showing us anything right now. We're just looking to see if it would show us, if that debug would show us why our neighbor relationship was not come up. What I wanted to see is if it showed the password or an authentication mismatch, because remember, our customer 1 router is performing BGP authentication with the password of Cisco, and ISP R2 we haven't set that up yet. So if we go under the neighbor statement again and put in the password of Cisco, what we should see is that we should see momentarily, we should see the BGP neighbor relationship form. The way we can check this is if we do a show IP BGP summary. This is going to give us our neighbor IP address. It's going to give us also the autonomous system that they are part of, messages received, sent, table version, which increments every time there's an update in BGP. We have another very important is up down. We can see it's never been established. And then also state and prefixes received is active. So this is not what we want to see right now. We know there's problems when you see this. Looks like we have in the log, we have a BGP adjacency change. So we're seeing neighbor of 12.1 as up. So if I go and do the command again, show IP BGP summary, we can see now instead of when we saw never, it shows the uptime. So 23 seconds. So now that we are seeing that we are receiving 2 prefixes from our neighbor, we can check that by doing a show IP BGP neighbors and do the command. We'll specify our neighbor IP address, which is 130.0.12.1. Then we'll put in the command routes, and we can see now these are the routes that we are receiving from the customer 1. Remember, those are the networks we're advertising with the network statement on customer 1. If I try to ping one of those networks, we can see that we have reachability now. We will go over this command and output in more detail. This is the network that we are learning via BGP. These entries over here mean that an asterisk is a valid, means that's a valid route. Sometimes you will see valid routes, but you will not have the caret next to it, which indicates the best route. So that means that there is a better path that BGP knows about rather than this one if you're not seeing the caret next to your route when you do this command. If you do not see the caret next to the prefix, then it is not being learned via that neighbor or populated into the routing table on the local router from that neighbor. And it's also given us the next hop, which is their external connection to our router, which is 12.1. And then over on the right hand side we have some of what's called the BGP attributes. BGP is a path vector routing protocol. It uses hop count, but it also uses a lot of other attributes to manipulate the best path through the network. So in this lab we'll probably look at the local preference attribute and the AS path attribute. The AS path attribute is basically your hop count inside of BGP. We can see path of 100. So that's how we know how to get to those networks, is through autonomous system 100. We can also specify weight, local preference, metric, and there's even a lot more. Again, in this lab we will just be looking at local preference attribute and AS path. So the next step is to go to ISP-R1, and we're going to set up the connection on ISP-R1 to customer 1. So we'll go under router BGP 200, which is the local autonomous system number, and then under BGP configuration mode we're going to put in the neighbor statement, which is going to be our peer that we want to establish an adjacency with, which is going to be 11.1. So we'll put in the IP 130.0.11.1, and then the remote autonomous system number of our neighbor, which is customer 1, which is 100. Again, this is specifying an external BGP neighbor relationship because it is not, this neighbor is not in our BGP autonomous system 200. Then we're going to put in the neighbor, we're going to put in authentication. So we'll put in the password of Cisco. We'll do a debug IP BGP events and see if we can catch any of this information. And we can't really see anything for the password authentication, but that is okay. If I do a show IP BGP summary now on ISP-R1, we can see that we now have a connection with customer 1, and that we are receiving 2 prefixes from customer 1. If I do a show IP BGP neighbor and then specify our neighbor IP address and specify the routes command, we can see that these are the 2 networks that we are at, that customer 1 is sending us. We can also do what is known as the received routes command. The only difference between received routes and routes, the received routes is the routes before it gets filtered by the local router, and then the routes is going to show you all the output after filtering has taken place. So if I'm the customer and I'm sending the ISP3 networks, but we're only seeing 2 on the ISP router, then we're asking ourselves, well, why isn't this 3rd network being routed? If we do a routes command and we only see 2 on the ISP router, we can do the received routes command and this should send us or show us if a third route is being advertised. So if we are seeing a third route in there, we might be filtering it on the local router from it being received on ISP R1 into the BGP table and routing table. So again, filtering before is received routes before it's filtered, and after it's filtered is the routes statement. So now let's go under router BGP 200, and we'll do this command soft reconfiguration inbound. That's why we saw the error before, inbound soft reconfiguration, that error. All we need to do is go under the neighbor statement to the neighbor and type in that soft reconfiguration inbound command. So that's all you need to do if you see that error. So right now it looks like both of the connections are good. So again, so far we've looked at BGP authentication, we've looked at internal BGP and external BGP. So now let's configure and talk a little bit about internal BGP. In order for all internal BGP speakers inside of to exchange routes with each other, they must be fully meshed, because if they are not, then you can create loops in your network, and you can think that external BGP uses hop count, where we use the AS path to determine, okay, we've already seen this is my autonomous system number, and if the ISP ever gets in the AS path an update, and I have my AS number in it from a neighbor, I'm gonna know to drop this. So the AS path is used for loop prevention, whereas internal BGP, when we peer with each other internally, we are peering using the same autonomous system number. So there's loop prevention with, we cannot use AS path attribute for loop prevention. So we must be fully synchronized with all of our IBGP neighbors. So every IBGP or every internal BGP router has to be peered with every other internal BGP router. Because if you are not, you're going to create routing loops, and that is not fun to troubleshoot. So what we are going to do is we are going to create IBGP connections between all of our routers. We are going to have ISP R3. We're going to call it a route reflector, and a route reflector is an internal BGP router that is used. Basically, ISP R3 is going to know how to get to every other IBGP router. This is a way to simplify your IBGP configuration by having one route reflector. So instead of R2 to be peered with R1 and R3, all it needs to do is peer with router 3. It's going to be the route reflector. It's going to know how to get to R1 and R2. So again, instead of R1 having to know about or have an IBGP connection with R2, it's going to peer directly with R3, which is going to be our route reflector. So you're creating a lot less IBGP connections, and you are simplifying your configuration. So route reflection allows us to do this within BGP. So let's go to ISP R1, and we will go under BGP for AS200, and we will do the command, the neighbor statement to ISP R3, and then the remote AS is going to be the same as the local AS, and this is going to be an internal BGP connection. And we're not going to have or be performing authentication within our internal BGP network, so we're not going to worry about BGP authentication between ISP R1, 2, and 3. So let's go to ISP R2 and get it configured as well. If I go under router BGP 200, and I'll do the neighbor statements. Right now, R2 is just peering with customer 1 router. We'll go ahead and peer with ISP R3. We'll do this with the neighbor statement, and then we'll put in the IP address of the link to R3, which is 192.168.23.1, which is the IP address of ISP R3. And then we're going to specify remote AS of 200. Again, internal BGP connection. So now let's go under router 3 and have it peer to router ISP R1 and ISP R2. We'll go under global configuration mode, do router BGP 200, and we'll do the neighbor statement towards ISP R1. We'll put in the remote autonomous system as 200. And then we will also specify our neighbor of 23.2, which is our connection from ISP R3 to ISP R2. So now if I do a show IP BGP summary, you can see we have peered with both routers now, with ISP R1, which is 13.1, and 23.2, which is ISP R2, both within the same AS with this AS 200. So let's go to all the routers. We'll go to ISP R1 and do a show IP BGP summary as well. You can see now that we have our neighbor connection to R3. Same with ISP R2. We now have the neighbor to ISP router 3. So now what we're going to do is we're going to set up BGP Route Reflector. Now we do not have a full mesh internally. We have not configured router 2 to router 1 or router 1 to router 2. So this is not a full mesh with internal BGP. So the first thing let's do is we'll go into ISP R2. We're going to advertise our loopback interfaces into BGP. And then once we do that, I will show you how to set up BGP Route Reflection, or a BGP Route Reflector. So we'll go under router BGP 200. Let's just verify that we have our loopback interfaces created. We can see that we have a directly connected loopback interface. If we want to advertise this correctly into BGP, we have to remember that we have to specify the correct mask, or it will not go into the routing table, our BGP topology table. So if we go under router BGP 200, we'll do the statement network. Actually, if we do a network 2.0.0.0, let me show you. Let's see what this looks like on ISP R2. If I do a show IP BGP on ISP R3, we do not see this. These links are our networks to customer 1. We're not going to worry about that just yet. What I wanted to show you is that we are not seeing the network that we just advertised via R2's loopback. Even if we do a clear IP BGP on the neighbor, which is 130, oh, I'm sorry, let's see, 130.0.23.2 soft. I'm sorry, not one. I'm sorry, 192.168.23.2. If we do a soft clear on our neighbor, if I do a show IP BGP now, we still do not see that route that we just advertised into BGP because it is not matching our entry in our routing table. This is matching the whole network, the whole 2 class A. So what we have to do is go under router 2 again. We'll do the command. We have to create the exact match prefix in order for BGP to advertise this route to neighbors. So we'll go under router BGP 200 on ISP R2. We'll do a no network on the 2 network we added, and then we will create the exact match now. So remember, in our routing table, our loopback is a /32 subnet mask. So we're going to add our mask, which is all 255s. So we have to put in the mask word there, is what I forgot. So let's put in our network 2.2.2.2 with the mask. And then of course this mask, which is the /32. So now that we have that, if I do a show IP BGP now on R3, we can see the loopback now being advertised to R3. So what do you guys think? Do you think R1 is going to have this network or not? If I do a show IP BGP, all we are seeing on R1 are the networks to our customer 1. So we do not see this because we are not peered with them, even though R3 is peered with R1. Router 3 is not going to pass these routes to R1 yet because we haven't set up R3 to reflect these routes, these IBGP routes, to its peers. So what we're going to do now is let's go in to router BGP 200. We will advertise my loopback interface. Let's go on to router 2 and just make sure that we can see this. Oh, I'm sorry. That is the wrong network. Let's go back under router BGP configuration mode, and instead of the 2 network, we put in router 2's, and we do not want to advertise that. We want to advertise our loopback, which is 3.3.3.3 with a /32 subnet mask. So now if I go to R2, now we can see the 3 network. And we should be able to ping and have reachability. However, on R1, router 1 can see the 3 network because, remember, this route is originating from router 3, so it's going to be able to see this because it has a pure adjacency to R3. But router 1 does not see router 2's because router 3 did not originate this route. So the next thing we want to do is, if on R1, if I do a show IP route, we will go under BGP configuration mode for AS200, and we will advertise our loopback on R1, which is network 1.1.1.1 with a /32 subnet mask. So now on router 3, if we do a show IP BGP, we can see both of those networks now, both of the loopbacks from R1 and R2. So if I do a show IP BGP, router 2 does not see router 1, and if I do a show IP BGP, router 1 does not see router 2's network. Now what we could do, just build a connection from R1 to R2 and R2 to R1, or we can set up what's known as BGP Route Reflector. So we can set up R3 to set up a route reflector on, and it knows how to get to all the IBGP neighbors, so we can use that to simplify all our BGP configuration. So again, this is going to lessen the configuration and the overhead on all the routers. So we're going to do this by going to ISP R3. We're going to go under router BGP 200, and we'll do the neighbor statement, which is our first neighbor. We're going to put in 192.168.13.1, and we're going to specify our command route reflector clients. So again, the client statement is going on the actual route reflector. So this is saying this is our neighbor, and he is a client of us. So this could kind of be looked at as a client-server relationship, where R3 is going to be the server and R1 and R2 are going to be the clients. We get an error, specify remote AS or peer group. So it's not taking it because I forgot to put on the 8. So now it's going to have to recalculate. So we're going to see BGP drop, and then it should come right back up. So now let's specify the route reflector client for the connection to router 2. So let's go ahead and add router 2 to be a route reflector client of router 3. We get the error down RR client, and then we can see it come back up. So we did not build, if we remember, a connection, an IBGP connection from R1 to R2 or from R2 to R1. We're using R3 as the route reflector. So now we should be able to see on R1's routing table the loopback interface that we added into IBGP from R2. And as we can see, there it is. And we have layer 3 reachability with the ping. So let's go to R2. We should see R1's loopback. And there it is. And we have reachability. So we have also successfully created a BGP Route Reflector using ISP R3. So that is a simple look, simple but very good demonstration of a Route Reflector client, our BGP Route Reflector. So our clients again were ISP R1 and ISP R2, and ISP R3 was the Route Reflector. We'll just add in IBGP RR just so that we know that that is our Route Reflector. Okay, so now the next thing we're going to take a look at is we're going to influence the routing from customer 1 out to the ISP. So what we want to do is we want to prefer the 45 meg link naturally because it is higher bandwidth. We want to prefer this link out to ISP R1 over ISP R2. We can do this in BGP by using the BGP attribute called Local Preference. So we can control our routing decisions on customer 1. If we do a show IP BGP on it, we see the local preference field and there's nothing on it yet. So we can use local preference to manipulate the way we want the traffic to flow out of our autonomous system. So it looks like we have two hops out to our ISP. We have our hop via ISP R1 and ISP R2. So right now we can see that it appears as though it is preferring the 11.2 hop and the 12.2. So what we're going to do on router 3, we forgot to add, if I do a show run, let's take a look at our configuration. Okay, so on customer 1, we can see that we are using, to reach the 2 and the 3 networks, we are using the hop of 12.2 indicated by the caret next to that, which is the hop over our T1, or the 1.5 meg link. So let's go ahead and see if we can verify this by doing a simple trace to the 2 network. and we can see it going out the 12.2 being the next hop, which is the point-to-point connection to ISP R2. So right now that is the way the traffic is going to reach this network. We can manipulate this by using the local preference BGP attribute. So what we'll do, the first step will go under global config. We'll create a standard access list 1 to permit any traffic, and we'll create what is called a route map. This can be used to manipulate all kinds of traffic for our routing protocols and other types of traffic on our router. We'll just create a route map named local preference. We'll do the permit option, and we have a lot of different options. What we're going to use for now is match and set. So what we're going to do is match IP address, and we're going to be matching our ACL that we just created, which is access control list 1. So match IP address 1, and then the next thing we're going to do is give an action on our match. So now that we've matched something, now we have to set the next statement. And so what we're going to do is we're going to see that we have a local preference option. So we're going to set the local preference to 5000. The higher local preference is going to be more preferred inside of BGP. So we're going to set the local preference in this case to 5000. For anything that is matching access list 1, in this case is everything, because access list 1 is permitting everything. So now that we've created the access list and the route map, we go under BGP 200, BGP 100 on customer 1, and under BGP all I need to do is specify the neighbor. In this case, neighbor 130.0.11.2. Again, that's our primary link path to ISP R1. We want to let that neighbor know everything inbound from that neighbor. We want to set the local preference to 5000. So all those routes from the ISP coming over the T3 are going to be more preferred than the T1 link. So we do this by specifying the route map, and then we're going to apply the route map we just created, which is local preference, and we're going to apply this inbound. So again, all the routes from the ISP into us. So again, that's the logic on the route map. It can be either inbound or outbound. In this case, inbound, we're going to set the route map to set the local preference to 5000 on all routes. So if I do a show IP BGP, the local preference is still blank. We're going to do what's known as a soft clear on the BGP neighbor. So we'll do a clear IP BGP 130.0.11.2, and then we will specify the command soft. So this will just reset the connection without bringing the neighbor adjacency down between the two routers. So any of the filtering that we've done, this clear should clear this connection and let these changes take place. So any filtering that you're doing, route manipulation, route maps, prefix lists, access control lists, always good to do a soft clear on the neighbor. So now when we do a show IP BGP, we can see the local preference value is now 5000. So we have the caret next to these routes now. So these are the preferred routes now to these destination networks. So the caret is what's being added into the routing table. and we can see that it is 11.2 now for all of our routes. So anything now coming inbound from our ISP, we are preferring over the T3 link. So all of our traffic going from the inside of our network to the outside. When we did this trace before to the 2 network, it went straight to ISP R2 via the T1 link. The 1.5 meg is the link in which it preferred before. So now if we do a trace to the 2 network, we can see that it is showing the link 130.0.11.2. So now it is choosing router 1. Looks like our trace is dying. Looks like there could be a problem in our network, and the reason that this trace is not being able to be completed is probably because we probably don't have a route in the routing table on one of our routers, and it might be those networks between the customer 1 router and the ISP. If I do a show IP BGP on R3, we can see there are no carets next to the 130 networks. Those are the networks that router 1 and router 2 are passing to R3, and they're not being added into the routing table. If I do a show IP route on R3, we do not have a connection to the 130 networks, the 1 and the 2/24s, because that is when the next hop, does not change within internal BGP. So what we need to do is go under our BGP connection to from R1 and R2 to R3. We have to set the next hop value to ourselves directly, because we can see the next hop. It sees 130.0.12.1, but it has no idea how to get to that network. So what we're going to do is tell router 3, okay, in order to get to those networks, you have to go through the ISP R1 and ISP R2. So we'll specify this under the neighbor statement under BGP on R1 and R2, and we'll put in the neighbor 192.168.13.2, and we'll specify the command next hop self. Let's also do this on R2. We'll go under global configuration mode. Then we'll put in we'll go under BGP AS200, and we'll put in the command neighbor 192.168.23. Let's see, from R2 to R3 we're using the 23.1, so neighbor 192.168.23.1, and then next hop self. So again, these routers, router 3 is the route reflector, so this is really going through R3 to get to the 2 network inside of our trace. So if we go back to router 3 and do a show IP BGP, we can see the caret next to these routes. It is seeing the more preferred path through 13.1. So now let's go to router 2. I'm sorry, not router 2. Let's go to the customer router and ping the 2 network. And what we can see is we still do not have reachability. So even though we have fixed the next hop self, problem, it looks like there's still a problem inside of our network that we need to troubleshoot. Let's go ahead and start that trace again to the 2 network and see if we can find out and pinpoint exactly where our problem is within this configuration. So now we're seeing the first hop, 130.0.11.2, and it looks like it is still timing out. And I believe the problem let's look at ISP R1. And do a debug IP packet. Let's see if this traffic makes it. So it looks like R1 is able to forward this traffic correctly. Let's do a debug IP packet on ISP R2. Okay, so it looks like we've pinpointed the problem right here with our debug IP packet. We are getting unroutable. So thanks to our debug IP packet commands, we are able to pinpoint the problem in our network topology. So let's go ahead and do an unall on both of the debugs. We are seeing unroutable now. And this is not good. Whenever you see unroutable when you're doing a debug IP packet, usually means that you have a big problem going on. It means your local routing table has no idea where to send this traffic. If we do a show IP route on R2, we do not know how to see the 11 network because we have not advertised that network into BGP. So the source of the trace is the 130.0.11.1 on customer 1. We do not know how to reach that network from ISP R2. That is why this traffic or this trace is not being able to be completed correctly. So let's go ahead and advertise both of those networks into BGP. So from R2 we're advertising the 12 network, which is the connection to customer 1, and then on ISP R1 we will add the network between customer 1 and ISP R1. So again, we're going to do that with the network 130.0.11.0 with a mask of with the /30 subnet mask. And now let's see, we can see the 11 network and the 12 network learned via BGP on ISP R1. So now if I do a show IP route on R2, we can see the 11 network now being learned by ISP R2. So now you can see that we can ping the 2 network now. And we have reachability. So what happens if we try to trace? Let's start the trace to the 2 network. Again, all we needed to do, we did a debug IP packet. We were seeing the packets were getting to router 2, but the return path was broken. It did not know how to reach the source of the trace, which was the 130.0.11.1, which was customer 1's interface. Again, that was the source of the trace. So yes, that will break your network. So we just added those networks to customer 1 on R2 and R3. I'm sorry, R2 and R1. We added those to BGP. So the trace is going out to R1. It's going to the hop between R1 and R3, and then its final hop is between R3, ISP R3 and ISP R2. So again, that's local preference, how to manipulate that BGP attribute. We can prefer traffic to go out of our network a certain direction. So the local preference value is carried throughout your IBGP network. It will mark this value and send it to IBGP peers. So the local preference value is very powerful in doing that. The weight value, the BGP attribute of weight, does not do that. It is effective only on the router that you set the weight for. So we have just influenced outbound traffic to the ISP from our local area network. So all traffic now is going out our primary 45 meg link. So the next thing we want to do is we're going to manipulate traffic from the ISP back to the customer 1 network. So if we do from ISP R2, if I do a show IP route or show IP BGP, we can see the 1 and 2 networks, the 130.0.1 and the .2, which is our next hop would be the 12.1, which is the T1 link. See how it has the caret next to that? So for the 10 and the 20, they both have the next hop as the 12.1 IP address. That's our external BGP connection to the customer router. So what we're going to do is, the last thing we're going to do in this lab is we're going to influence traffic. We're going to influence the ISP's decision on how to reach the customer 1 networks using the BGP AS path attribute. So we're going to make it look like this link is a lot farther away than it really is. So we're going to perform this configuration on the customer router. We're going to create a route map. We will name it AS_path. We're going to permit. Then we'll just match. And what we want to do, you can change this if you want, but what we're going to do is we're going to match everything. We're going to match IP address 1, which is our access list on this router that matches and permits all traffic. And when we match this ACL, we're going to use the set command. We're going to do our action. So now that we've matched it, we're going to perform the following action. We're going to set, and we're going to use the first option, which is AS path. We're going to prepend our AS. So we'll do set AS path prepend, and then we're going to put our autonomous system number in. We'll just do that 6 times, and I'll show you why we're doing this in 1 second. Let's take a look and make sure we have the access list still created on customer 1. We have ACL 1, which is permitting all traffic. So we're going to go under BGP on customer 1, and we're going to put in the neighbor. Again, this is going to be our T1 neighbor, so 130.0.12.2, and we're going to specify our route map that we just created, which is AS_path. And what we are going to do is, again, we have the direction, inbound or out. We're going to send this out. So we are sending this information out to our ISP via our BGP updates. So basically what this is going to do is send this to ISP R2. It's going to make it look like we have prepended, or there is more autonomous systems in the path that are actually there. So again, it's a BGP path vector protocol. It uses AS path to determine our hop count, to determine the best path through the network. So in this case, we're going to make it look like we're farther away than we really are, because we want this traffic to be flowing inbound from the ISP to customer 1 over the connection, over our 45 meg connection, which is ISP through ISP R1. So we'll go ahead and hit enter on that command and get out of there. And now we'll go back to R2. So this is the path is the AS path. If we can see on the right hand side, we're only seeing 100 right now. We're only seeing 100 right now. If I do a clear, we'll clear our neighbor relationship to customer 1. We'll do a soft clear on that and see if we can see. And now if I do a show IP BGP, we can see the AS path prepending that we wanted to do. So now it is showing in the path 1, 2, 3, 4, 5, 6, 7. So now it looks like there is 7 hops across this next hop to get to those networks. Whereas before we're reaching the 12.1. So now if we go down and look to reach the 1 network, 130.0.1.0, it's showing the next hop of 13.1. And that is our connection to ISP R1. Same thing with the 2 network. We are now seeing the next hop, or the best path to get to this is going to be through ISP R1 instead of our directly connected BGP connection to customer 1. So we're only seeing 1 AS in the path, whereas now for this other one we are seeing 7. So now what I'm doing is I'm doing a trace to the 130.0.1.1. Right now I'm doing a trace, and I have a debug set up on customer 1, and I'm getting unroutable traffic. So the last thing I'm going to show you in this lab, I know it's been a very long lab, what I'm going to show you is how to configure what's called a default route within BGP. So all this traffic is being black holed on the customer 1 router. So this is very easy to do within BGP. On ISP router 1 and 2, we will specify the neighbor connection to customer 1, which is neighbor 11.1, and we'll just put in the option of default originate. So again, let's go to ISP R2 under router BGP 200, and we are going to point towards our neighbor connection to customer 1, which is the 130.0.12.1, and we will put in the default originate command. So now if I go into customer 1 and do a show IP route, we are now receiving a BGP default route indicated by the B and the asterisk. So any traffic that the router does not know how to send it to, it's going to send it out the default route. So that is how you add a default route via BGP. That's one of the ways you can do that. One of the simplest. So we're going to go to R2 and try to ping this one network off of customer 1, and now you can see that it works. So let's go ahead and try to trace now to the 130.0.1.1 network, and let's see if our trace makes it through now. Whereas before we were seeing unroutable on customer 1. So we are prepending over the T1, so this should prefer the T3 link between ISP R1 and customer 1. So we can see the trace going to 12.1, then we can see it going to 23.1, and we see the 13.1 connection. So we're seeing the 23.1, which is our connection to R3, ISP R3. We're seeing the 13.1, which is the connection between ISP R3 and ISP R1. And then we are seeing the 11.1, which is our connection to customer 1 from ISP R1. So we have manipulated inbound traffic now from the ISP network to the customer networks. So we manipulated also outbound traffic from the customer out to the ISP using local preference. So thanks again for watching this video, and I hope to see you in the next one.